Hi guys, happy Tuesday. Well, actually it's Sunday when I'm recording this. But it's Tuesday now that you're watching it. It's a little rainy outside right now on Sunday. It's thundering a little bit. So if you hear some thunder, that's what's happening. Okay, so this week, we are going to talk a little more about sequences and series. Last week was just very general, some vocab, just to kind of give you an idea of what a sequence is, what a series is. But there's two that are particularly important, and we're going to talk about the first one of those two this week. So the first one that we're going to talk about this week is arithmetic sequences and series. So you're going to get some specific rules and formulas for that particular type of sequence or series. So let me switch over. Share my camera. And move myself out of the way. Okay, so I need to back up a little bit. Sure, we're all focused in here. Okay, all right. Arithmetic sequences and series. Okay, so first thing we have to talk about is the definition of this specific kind. So what even is an arithmetic sequence or series? So we're going to start with the sequence first. So if you remember last week, the sequence is just listing out the numbers, where the series is adding them all up as we go so that we get one grand total. So we're going to sort of go in that same order this week. So we're going to talk about the sequence first. So arithmetic sequence. So the definition of an arithmetic sequence, the thing that makes it arithmetic, if you kind of think about the name, it sort of reminds you of the word arithmetic, right? Which means, or just, I mean, I guess technically it is that word. We're just pronouncing it differently. But it means that we're adding or subtracting the same number every single time to get the next number in the sequence. So we would define it as a sequence in which the difference between consecutive terms is constant. So to get from one number to the next in our list of numbers in our sequence, we're just adding the same amount every time or subtracting the same amount every single time. So we might be like adding 2 and then we add 2 again and then we add 2 again, or we go from 1 to the next by subtracting 5 every single time. The difference between the terms is constant, and sometimes that is called the common difference. And you'll notice that in the formulas that we're going to use in just a second, it's going to be denoted as D, as a lowercase d. So we're going to do kind of two things with the sequences. Well, actually, well, yeah, I guess two things with the sequences, where most of the time you are going to be given some information about the sequence, and then you're going to be asked to find the rule or the formula, and then probably also find a specific term number. So like, you know, they might give you the first 3 numbers or 4 numbers in the list, and then they'll say, write the rule or the formula for this sequence, and then find the 75th term. Well, you don't want to have to keep like adding or subtracting the same number over and over and over again until you get all the way out to the 75th term, right? That's, I mean, you could, but that is not very much fun. So we're going to talk about sort of some shortcuts on how to come up with a formula that will just let you plug a value in and figure out the term that you're looking for. That's what you saw in the video last week. We were able to just say, oh, we want to find this term, so we're going to plug in this number and work it out and see what we get. So we are going to talk about finding the nth term of an arithmetic sequence. Okay, so last week in the video, we talked about two different types of formulas. We had an explicit formula and we had a recursive formula. So if you remember, explicit just like gives you the rule and it has like an n or an x or whatever in there. And if you want to find like the 4th term, you just plug in 4. If you want to find the 20th term, you just plug in 20. The sort of flip side to that was the recursive formula. The recursive formula was the one that started by telling us what the first term was and then told us how to get the next term from that. So we're going to look at those same two things again, explicit formulas and recursive formulas, but they're going to be specific to the fact that now we're talking about an arithmetic sequence, okay? So I'm going to start with the explicit formula. So I'm going to sort of write this down and then we'll talk about what the notation is. So we have a sub n equals a sub 1 plus n minus 1 times d. So given that we saw some of this stuff last week, you could probably figure out what some of this notation is. So a sub n is just the nth term, right? Like if this is a 5, that means we're calculating the 5th term. If this is a 10, we're calculating the 10th term. So this is just whatever term we're looking for. A sub 1, that's the first number in the list, so we have to kind of know the first number. Well, we don't have to. We're actually going to do some in just a second where we don't know the first number. But we need to know other stuff to get around that. But a sub 1 is the first number in the list. We already mentioned a second ago, D is going to be whatever that common difference is. So whatever we're adding or subtracting every time to get to the next number. And then n minus 1, remember from last week, this n is the same value as whatever this subscript is over here. So like if this was a 5, then this n value would also be a 5. Now in just a second, when we write just the generic rule, when you have your rule or your formula, the n is still going to be in there. We're not going to actually plug in a number for that if we're just kind of finding a generic rule. But you'll see that in just a second. That'll make more sense in a minute. So this is how we're going to set up to find an explicit formula for an arithmetic series. And then if the question asks us to find a recursive formula, we have a way to do that too. So remember, recursive, the first thing that we have to do is to state what the first number is in the sequence. So we need to say what a sub 1 is. And then recursive, if you remember from last week, we just take that, we take the previous term, and since this is arithmetic, and that means we're adding or subtracting the same number every single time, then to get the nth term, we're just going to take the previous term and add or subtract whatever that common difference is. So for instance, if I wanted to find the 10th term in my list, I would just take the 9th term and add whatever the difference was, or subtract whatever the difference was. Now this one's a little bit harder because you kind of have to go one number at a time, right? To get the 9th number, you have to know the 8th number, but to get the 8th number, you have to know the 7th number, and then to get the 7th number, you got to know the 6th number. So this is a little bit more annoying because, you know, if you were going to write it out, you'd have to know all the numbers. Explicit is really nice because if you just want to figure out a certain term number, you can just figure it out. You don't need to know all the stuff that came before it. We can just say, oh, if I want to find the 50th term, then I've got this rule that lets me just plug in 50 and work it out. As long as I know the first number and the common difference, I can come up with a rule. So explicit is a lot more user-friendly when you're trying to find a certain term number. It's a lot faster than using the recursive, because with recursive, you got to find like every single number leading up to whichever one you're looking for. Okay, so let's do some examples so you can kind of see how this works. Okay, so we are going to be given this sequence, 50, 44, 38, 32, and so on. And we want to do two things. We want to write the rule, and we want to find a sub 20. So we want to find the 20th term. Now this is kind of generic. It just says write the rule. It doesn't really say which one we're supposed to do. Most of the time, textbooks and things will have you looking for the explicit formula. We're actually going to do both. But we're going to start with the explicit formula. So if we look back up here, this was our rule. So I'm just going to sort of recopy that. A sub n, first term, n minus 1 times the common difference. So we have to sort of look and see what we already know, right? So A sub n, we know the first term, that's 50. N minus 1, that's just going to stay that way, because remember, we're trying to find just sort of a generic formula that we can use for anything, that we can use for any term number. So a lot of times people sort of get confused and they really, really, really want to put something in there for the n value. You're only really going to do that when you're finding a specific thing. Like we're going to do that when we get to this part and we're finding this term. But if you're just writing the rule, you're just writing a generic formula. So we're going to just leave n alone for right now. It's just going to stay in n. And then we can look up here and we can see, well, what are they doing each time to go from one number to the next? They're subtracting 6 every single time. So our common difference is going to be a -6. Negative because we're subtracting. And so then we just have to sort of work this out and kind of simplify it a bit. So we've got 50. If I distribute my -6, this is going to be minus 6n plus 6. So then I'm going to get a sub n. I can add these together. So this is going to be 56 minus 6n. Or if you wanted to write it the other way, you could say -6n plus 56. That's fine. Nothing wrong with that. So this is my rule. This is my generic rule. And now I can use this to find any term I want. I could find the 10th term. I could find the 400th term. Doesn't matter. We're asked to find the 20th term. So I'm going to come over here and I'm going to find the 20th term. So according to this, remember we said for the rule, this n value, whatever the subscript is, that's the same value as this n over here. So if I'm looking for the 20th term and this number, this subscript is 20, then that means this n is going to be 20 as well. I'm basically just substituting 20 into my formula to figure out what my 20th term is. So -6 times 20. And if we work this out, I think we get -64. So we have to sort of think about, does that make sense? Does it make sense to think that the 20th term is going to be negative 64. Well, that should kind of make sense to you because we're subtracting 6 every single time. So eventually, if we keep subtracting 6, we're going to go into the negative values. And then we're just going to keep getting more and more and more and more negative. So it kind of makes sense that this is going to end up being a negative number, right? Because eventually down the line, you're going to keep subtracting until you get to those negatives. So this was our explicit formula. Now, if I wanted to write this recursively, I could do that as well. If we slide back up here, we need two things to write the recursive formula. We need to state what the first term is, and then we need to state what do we do to get to the next one. So if I come back down here, if I wanted to do a recursive, I just need to state the first term. So the first term was 50. And then I need to say, okay, if I want a sub n, I just need to take the previous term and subtract 6. So this is my recursive rule or recursive formula. It's got two parts to it. You got to have both parts. If you tell me the rule over here, if you tell me you're subtracting 6, but you don't tell me where you're starting, it's kind of useless, right? I have a lot of people, I did this with my IB class, and I had some people that would give me this part, but they wouldn't tell me where to start. So that's not super helpful, right? We got to have both pieces to this. Okay, so let's look at another one. Okay, so we want to find the 13th term of 2, 6, 10, 14, 18, and so on. So I'm going to go through this one. If you want to pause the video, you can do that and then come back and see if your rule matches mine. So I'm going to start with my formula here, and I'm just going to fill in stuff. So the first term is 2. This is going to just stay n minus 1. It looks like we're adding 4 each time, so that's going to be a positive 4 for my common difference. And then let's see, we're going to have 2. This is going to be 4n minus 4. So it looks like my rule is going to be negative 2 plus 4n. And then we wanted the 13th term. So 13th term. So 4 times 13 minus 1. I think our 13th term should be 50, I believe. All right. If I wanted to write the recursive formula, so again, we can label this as explicit. If I wanted to do recursive, I could say the first term is 2. And then every time I want to get a new one, I take the previous term and add 4. Okay. Now, what if they give you some different information though? Because so far for both of these, we've just started off at the beginning of the sequence, right? We knew the first number. So what if they give you a different combination of information? Cords are getting in my way here. Okay, so let's say we want to write the rule for the sequence whose 8th term, oh, you can't see that, whose 8th term is 50, and our common difference is 1/4. All right, so if we think about our rule, we know our common difference, right? They told us that, but we don't know the first term. We know the 8th term. So we have to do something a little bit different for this one. So let's see, I'm gonna make this a sub 8 because we know the 8th term. We're gonna replace this in just a second. We don't know the first term, but remember we said this n and this n should always be the same value. So 8th term, that means this is gonna be 8 minus 1. I know my common difference is 1/4. Now remember what it said in the problem. It says the 8th term is 50. So I know that a sub 8 equals 50. So I can replace this and just say, oh, that's 50. Some of you can probably just jump straight to that and just have the 50 and like not even put this line in here. But sometimes when I leave this line out, people get very confused because if I just jump straight to this line, sometimes people are a little confused as to like why I put the 50 there and why I put the 8 over here. But I think adding this line in the notes, especially at least, kind of shows you where those numbers come from. So I'm just saying, oh, the 8th term is 50, right? Those are equivalent, so I can replace one with the other. And then this is an 8 because this n value has to match this n value here. So now I can actually solve this for my first term, and then I can go back and write my rule. So if this is going to be 7, if I go ahead and subtract those, this is going to be 50. This is 7 times 1/4. If we work all this out, our first term turns out to be 48 and 1/4. So now I could go over here and I can write my rule. So a sub n, my first term I know is 48 and 1/4. This is going to stay n minus 1. We know our common difference was 1/4. And if you distribute your 1/4 and you simplify, move some stuff around, you should get 48 plus 1/4 n. So this is our rule. This is our explicit rule. And now, if we wanted to, we could also go back and write the recursive rule because we have the first term and we know the common difference. So I could also write my recursive rule if I wanted to. Let's see, another similar one to this. If you're given that the 13th term is 30 and the common difference is 3/2, means we're adding 3/2. We want to write the explicit rule for this sequence. So I can sort of set this up the same way. I know the 13th term, so if I make this a sub 13, don't know the first term, but then this is going to be 13 minus 1. I know my common difference. And then I'm going to simplify a little bit. We know the 13th term is 30, so I can say, okay, this is 30. This is a sub 1. This is going to be 12 times 3/2. And so if we simplify that a little bit, we're going to figure out that our A1 is 12. And then if I want to come over here and write my explicit rule, my first number is 12. My common difference is 3/2. I'm going to distribute my 3/2, simplify some stuff around, and I believe this one turns out to be 10.5 or 10.5 plus 3/2 n. So then for both of these, this one up here and this one, now that we have this explicit rule, we could find any term number we wanted, right? We could find the 50th term by just plugging 50 in for n in either rule, or we could find the 75th term or whatever. Okay, that explicit rule, once you know that explicit rule, makes it really super easy to find any other term that you're looking for. All right, another type, really quick before we move on to our series stuff. What if you're just given like 2 random terms somewhere? So for instance, the 20th term and the 15th term. And same thing, we want to write the explicit, did I do explicit on this one? Yeah, explicit rule. Okay, so there's actually a couple different ways you can do this. You can, I'm going to show you one way and then just sort of talk about the other way. So one thing that you can do is use each one of these to set up kind of an equation or a partial rule. So I can set up a rule or an equation with this one, and then I can set up a different rule or equation with this guy and almost do it like a system of equations. So this is going to look very similar to what we did up here with these two. Remember, I slide back up here, we said, okay, since we knew the 13th term, we could put that here, and then this also was a 13, and that became a 12. So I'm going to sort of do the same thing that I did up here and try to write an equation that's just missing that first term. Okay, it's also going to be missing the common difference because we don't know what that is down here in this one either, right? So I know that the 20th term is 240. So I'm going to start with that. I don't know the first term. Remember the next bit, this is where my n minus 1 would go, but my n is 20. So that means that when I get to here, n minus 1, that's going to be 19. And then I don't know my common difference. Then I can set up something similar with this one. The 15th term is 170. So I can put that over there. Just don't know the first term. This is where my n minus 1 would go. But n is 15, which means n minus 1 is going to be 14. And then I don't know my common difference. So you could do this as a like a system of equations. So I could set this up and subtract these, because what's going to happen is when I subtract these, my A1s are going to cancel out. So 240 minus 170, that's going to be 70. These are going to cancel out. A1 minus A1. 19D minus 14D is 5D. And then if we divide, we're going to figure out that our common difference is 14. And then you can take that and plug it back into either of these guys up here to figure out your first term. So if you do that, its first term turns out to be negative 26. And then I can use that. I can use both of these things to come over here and come up with my rule. So I've got negative 26 n minus 1. My common difference is 14. And then if I work all this out, my explicit rule turns out to be something like that. The other way to do this, I won't work out through the whole thing, but there is another way to do this where you sort of look and you sort of think, okay, so this is the 20th term, this is the 15th term. If we look at the difference between these two numbers, kind of did that down here, right? Difference between these two numbers is 70. And the difference between these positions, this is the 15th term and this is the 20th term. So there's a difference of 5 in their positions. So if I take this total difference between these two numbers, that's 70, and I divide it amongst like the 5 positions, the 5 numbers that have to be in between this guy and this guy, like the 16th number, the 17th, the 18th, 19th, 20th, then you can figure out the common difference that way. You can sort of do it in your head without having to kind of write it all down as the system of equations. Some people like the system of equations just because it's like a set thing that you can do every time that's going to work. And they like to have kind of the formula aspect to it. But you can also just kind of think about what's happening with these numbers, right? There's a difference of 70, and that's spread out over basically 5 positions from the 15th number to the 20th number in our list. So that means if we split that up evenly, that means we're going to be adding 14 every time to make that happen. So either way you want to do it, you can figure out the common difference, figure out that first term, and then you've got your rule. I'll give you another one to do, just if you want. I'll set it up for you and then just kind of tell you what the final answer is going to be. So for this one, we've got the 8th term is 75. The 20th term is 39. And then you have to come up with the explicit rule. So for this one, you should figure out however you're doing it. If you want to do it system of equations, if you want to just kind of do it in your head, common difference turns out to be -3, which means that the first term in our list ends up being 96. And if you put all that together, your explicit rule turns out to be 99 minus 3n. So you can sort of do that one if you like as some extra practice. Okay, moving on to the series stuff. Arithmetic series. So again, the only difference between a sequence and a series is that when you do the series, you're adding up all of your numbers as you go. So you're going to get like a grand total. So this is just the sum of the terms in an arithmetic sequence. Okay, so the first thing that we're going to talk about here is how to find the sum of a finite arithmetic sequence. Remember, finite means it stops somewhere. It has an ending point. You can have an arithmetic sequence, actually, sorry. This should say series, arithmetic series. You can have a finite one that just goes on and on and on and on and on forever. You can have a infinite, I think I said that wrong. Infinite is what I meant to say. You can have an infinite arithmetic sequence of numbers where, you know, let's say our common difference was 5. We just keep adding 5 to get the next number, add 5 again to get the next number, add 5 again to get the next number. And it just goes on that way forever, right? The problem with that is, though, that because it just goes on and on and on and on forever, and our numbers are just going to keep getting bigger and bigger and bigger because we're adding 5 every time, we can't find a sum of that because it's just going to keep getting bigger, right? If we're adding 5 every single time, then, you know, we'd have 5 plus 10 plus 15 plus 20 plus 25 plus 30 plus 35 plus 40 and so on. And our sum the grand total just keeps getting bigger and bigger and bigger and bigger and bigger. And it's just not going to approach a single value, right? That would be like a diverging thing, right? From the last video, we talked about diverging and converging. So if it goes on and on and on forever, it's divergent. It just doesn't approach a single value. Our grand total just keeps getting bigger and bigger and bigger. But if we have a finite list of numbers, we can add those up. Now, obviously, if our list of numbers is super duper long, we would like to have kind of a shortcut way of doing that, right? So there's 2 different formulas that we're going to look at here. So there's one that looks like this. So let me write this down and then we'll talk about what all of this is. So there's this one. So S just means sum. N is the number of things that we're adding together. So if this were a 7, we would be adding together the first 7 terms of the sequence. This is the same. This N is the same as this. So this is how many things we're adding together. This is the first term. This is going to be the last term that we're adding up. So again, if this was 7, then this would be a 7 as well. We're adding 7 things together. This would be the 7th term in our list. A sub 7 would be the 7th term in the list. And then obviously 2 is 2. So this is what we're going to use. Use if the first and last terms are known. Okay, you gotta have certain pieces of information to use that particular formula. But there's another formula that we can use if we are given slightly different set of information. So there's another one that looks like this. N divided by 2 a little bit. Okay, so the second one, notice it's a little bit different. It uses some different information. We still have to know how many things we're adding up all together. That's our N. But we only need to know the first number in our list and the common difference. We don't need to know what the last number is in the list of things that we're trying to add up, okay? So this one, we're gonna use if the last term is unknown. So depending on what they give you in the problem, you kind of have 2 different ways to approach it. You got 2 different formulas that you can use depending on what you know about your sequence or your series. So let's look at some examples. All right, so we want to find the sum of -5 plus 2 plus 9 plus ... plus 317. All right, so we're adding up this list of numbers, but we don't even kind of know all the middle numbers, right? We just like skip over them. But that's okay, that doesn't matter. We don't really need to know those. What we can do is we can use this guy up here. We're also missing, actually, I misspoke. We do need to know how many things we have, right? We need to know the number of things that we're adding together because both of these have this n in them. So we need to know how many things we're adding together. So we can do that first. We can figure out what our n value is going to be. We've got enough information here to figure that out. So let's do that first. We need to know the number of terms. So let's think about this. We have this rule from before. We can figure this out. We know our last term is 317. We know our first term, -5. We don't know n, but we can look and figure out the common difference. We're just adding 7 each time. So if I solve this for n, I believe it turns out to be 47. So in this list of numbers, starting from -5 going to 317, there would be 47 numbers. So we skipped over quite a few in that little dotted section. So now we can kind of go over here and we can use this first formula that we had. So we're finding the sum of 47 values. So n is 47. Our first number is -5. Our last number is 317. We're gonna add those together, divide by 2. So if I work this out, our sum turns out to be 7,332. So adding up all of these numbers, even though we don't even know what some of these numbers are, we can still get a sum. A similar problem, find the sum of the first 100 integers. So we want to do sum of 100 numbers. So our n is 100. 1 plus 100 over 2. Our first number in the list would be 1. Our last number in the list would be 100. If we work all that out, we get 5,050. If we look at some that would use the other formula, we would have something like this. So let's say we have 4, 7, 10, 13, and so on. And we want to find the sum of the first 30 terms. So they only give us the first 4 though. We don't know what the last one is going to be. Now, I suppose we could just keep adding 3 and fill out that list until we get to the 30th term and add them all up, or then use the first formula that we were looking at. But remember, we have this other one that says that we can use this other formula even if we don't know what that last term is going to be. So if we're looking for the first 30 terms, if I look at that second formula, it says n over 2, so this would be 30 over 2. And then I've got 2 times a sub 1, that's going to be 4, plus n minus 1. So remember, n in this case is 30. We have n here and n here. So 30 minus 1, and then our common difference. So I can see here that we're adding 3 every single time. So if I just kind of do the math on that, this is going to be 15. This is going to be 8. This is 29 times 3, whatever that is. Add the 8, multiply by 15. If we work all of that out, we can get a grand total of 1425. So we don't even have to know what all the terms are. We've got this formula that will let us figure that out. Sometimes they'll write problems like this. I think in the video from last week, I mentioned very briefly the idea of a partial sum. So they might say something like, find the 18th partial sum of, and then they'll give you some numbers. So we're adding these up. We want to find the 18th partial sum. That's just a fancy way of saying add up the first 18 values, or the first 18 terms in this series. So this is just S sub 18. So we would set this up the same way we just did the previous one. We'd have 18 over 2. First number is 100. Let's say we've got n minus 1, so that's going to be 18 minus 1. Our common difference, adding 10 every single time. So then we just work that out. And I got 3330 for that one. All right. Now, last little bit. We talked last week about, excuse me, here, Drake. About sigma notation. So sometimes you will see these presented in sigma notation as well. So let's take a look at a couple of those so you can see what that looks like. So you might have a problem that looks like this. We have our big sigma. We have n equals 6 on the bottom. We have 28, and then they might give us this rule, 5n minus 17. So remember, this is our rule for our series. This is the number that we start with when we start to plug things in for our n value. So I would start with 6, work that out, and then 7, then 8, then 9, then 10, all the way up to and including 28. So what's happening here, and you don't necessarily have to write this out for every single problem, but just to make sure that we're clear on what's happening, is we are plugging in 6 into this rule and then saying plus, plugging in 7 into this rule, then 8, then 9, then 10, all the way up to 28, right? That's essentially what this notation is saying. This is a nice shortcut way of telling us that this is what's happening, right? We're plugging in these numbers into this rule, and as we go, we're adding everything up as we go. So if we were to work all of this stuff out, if I worked this part out, this would be 13. If I worked this one out, I believe that's 18. All the way up to the very last one. If I work this out, I believe that's 123. So it's basically asking us to add all of these numbers up, right? So we now have a formula for how to do that. Now you have to be a little bit careful with this notation because we have to think about how many numbers are we adding up here when we're doing this, right? We're starting with 6, we're plugging in 6, then 7, then 8, then 9, then 10, all the way up to and including 28. So what happens is a lot of times people just subtract these, right? 28 minus 6 is 22, but that's not exactly right because you're not counting the 6 that you started with as your first value that you're plugging in. If you actually count it out on your fingers, start with 6, then 7, then 8, then 9, then 10, 11, 12, all the way up to 28. That's actually 23 terms that you're adding up, not 22. So be careful with this notation. You can't just subtract these two things. You have to subtract and then add one back, because if you just subtract, you're not counting this first number here, right? You're figuring out the difference between them, but that's not what we want. We want to know how many terms there are. So there's actually 23 terms that we're adding up. So I'm going to use that first formula that we wrote down. So my n value is 23. I know the first number in my list is 13. I know the last number in my list is 123. So I can plug those into that guy and I can work out my total sum. Now you do have to do a little bit of work, right? You don't necessarily have to write all of this out, but you at least have to figure out your first number and your last number to be able to use this formula. So you have to figure out this little bit right here where we plugged in the 6 and this little bit where we plugged in the 28, because I need to know my first number and last number. And then we also have to think for a second to figure out how many terms there are that we're adding up together. All right, so let's do one more of these. If you want, you can pause this and do this on your own. Okay, so there's my problem. I've got a rule. I'm starting with 23, going all the way up to and including 37. So I have to think about how many terms I'm adding up. So if I'm going from 23 to 37, remember you can subtract these, but then just remember to add one back to it to account for this starting number. So if I subtract these, I'm going to get 14. Add one back, that's 15. So I'm actually adding 15 terms together. So that means my n is 15. I'm going to need to know my first number and my last number. So the first number is going to be whatever I get when I plug 23 into this rule. So I plug that into there. That gives me 49. So that's my first term. I need to know what my last number is. Well, my last number in my series is going to be whatever I get from plugging in 37 into my rule. So that turns out to be, I believe, 77. So if I do my little formula here, work that out, I get 945. 945. And then I'm not going to work all of this one out, but I'll at least give you this for those of you that want one more to practice with. So we're going to start at 12 to 18, negative 2n plus 57. That's our rule. So the grand total after everything, I believe, is 189. So you can see if you can work that one out and get a grand total of 189. All right, let me stop my camera here. Whew, okay, hope you guys are doing well, hanging in there. Just got a few weeks left. That's crazy. So You guys are going to have some homework to go along with this. It'll be in Alex. It'll just be like another homework thing. Remember, with the homeworks, you have multiple attempts. So if you get some wrong, you can go back in and fix those. You don't have to redo the whole thing. For the homeworks, I usually set them up so that you only have to redo the ones that you got wrong if you do want to go back in. If you're like, I missed one, I got like a 90 something, and you're like, it's just homework. That's fine. Live with your 90 or whatever you want. But if you do want to go back and try to fix the ones that you missed, you can do that. So, okay. So video for this week, Alex homework, and I think that's it. So I will see you guys next week. I miss you all, and let me know if you need me. I'll be doing my Tuesday afternoon check-in, hang out, if you want to just stop in and say hi. Okay, bye guys.